In this video, we're going to continue talking about some control systems, but we're going to start talking about building control concepts. And we want to talk a little bit about devices and signals and some terminology before we start digging into the details. Control device, we're going to consider as a building automation device that monitors or changes system variables, makes control decisions, or interfaces with any other type of system. A control device can include sensors, controllers, actuators, and human-readable or human-machine interfaces. A variable is just that. It's a changing characteristics in the system. Could be temperature, could be pressure, could be position, could be anything we are trying to monitor. A sensor is a device that measures the value of a controlled variable. Temperature, light, humidity, pressure, location, distance, can be anything. The sensor output signal is electrical. Voltage or current could be air pressure, could be optics as in fiber optics, or could be a radio frequency. Sensors are considered input devices. Now let me quickly explain that. When we talk about any device being an input or an output device, we are looking at it from the standpoint of the controller. The sensor must be located where they can properly read the control variable. Sensors are selected by sensor type, range, resolution, accuracy, signal type, which we'll talk more about in a minute, cost, and power usage. While the second to last one, cost, is not always the most important, it's something that has to be taken into mind. The more accurate, the higher the resolution, the further the range, and the lower power usage, the more the sensor is going to cost. You get what you pay for. Higher quality costs more money, but in the long run is a better product. Electromechanical sensors use a mechanical means to measure a variable. They then convert that mechanical motion to an electrical signal to send to the controller. It can measure pressure, position, and fluid level. Can also mention speed sometimes, but most often pressure, position, and fluid level. Electronic sensors do not have any moving parts. They are smaller than electromechanical sensors. Measurements happen by solid state changes. For example, in a thermostat, the resistance changes when the temperature changes. Sensors are all connected to terminals on the controller. A controller is a device that makes decisions to change some aspect of a system based on the sensor information and internal logic programming. A controller receives a value from the sensor, compares it to a desired value, sends an appropriate output signal to an actuator. Controllers are sometimes less rugged than the sensors, and they may need to be installed in a protected environment. In other words, you probably don't want to install a controller where there's a lot of dust, where there's a lot of dirt, where there's a lot of moisture. They have circuit boards in them and are electronic devices. Some controllers are designed for specific purposes, for example, climate control. And some controllers are designed for more general purposes and are considered generic. Generic controllers are more flexible. They'll do climate control, they'll do lighting control, they'll do access control, but they require more programming to achieve the desired functionality. Actuators are an output device. They accept a controlled signal and cause a mechanical motion. This motion can control a damper, a valve, or a switch. It can change a position or cause some other change that will affect one or more parts of a system. An example is an actuator may open a valve allowing cold water into an air handler coil, thus cooling the air blowing across it. Air conditioning. Common types of actuators are relays, solenoids, and motors. A relay is an electrical switch that is actuated by a separate electrical circuit. What this does, it allows a low voltage control circuit to open and close contacts in higher voltage load circuits. Some are electromechanical. They have moving parts, and some are solid states with no moving parts. All depends on the need and the load voltage. That's the high voltage. A solenoid is a device that converts electrical energy to linear mechanical force. Solenoids are typically used in quick-acting valves to open or close, or for locking and unlocking doors for access control. Okay, solenoids have a coil, and they usually have a plunger. Coil is energized, plunger extends or contracts. Okay, depends if it's normally open or closed. Electric motor is a device that converts electrical energy into rotating mechanical energy. Electric actuator motors can be used to turn something completely open or completely closed or to any point in between. They're most often used to actuate dampers and valves. Human-machine interfaces, are connected into building automation systems to allow people to view and modify the controller information. HMIs, which are the initials for human-machine interface, are normally hardware or software controlled. Many, and I used to say may, but actually most these days, include programming to provide a web interface where a technician can access, view, and change programming information from any computer that's connected to the network. Now, a web interface is also known as a thin interface. There are heavy interfaces as well, but that requires software to be installed on a technician or a human interface. Now, what happens? What is sent from a controller to the output or from an input to a controller? They're called control signals. A control signal is a changing characteristic that is used to communicate building automation information between a controller and a controlled device. These control signals are most often electrical, but can also be pressure, light, and radio frequency. There are different types of controlled signals based on the different needs of the system and the type of the controller. Three common types of control signals exist. We have digital, we have analog, and we have protocol messages. Digital signals are a signal that has two possible states. They're either completely on or completely off. The most common is 0 volts DC is off and positive 5 volts direct current or DC is on. This is the same voltage level that is found in most laptop and desktop computers. All connected devices must use and expect the same voltage levels. So once you decide on 0 and positive 5, everything on the system must use and understand 0 and plus 5. Voltages has to be constant. Okay, you can't go from 6 to 1 to 4 to 3. Changing levels in a digital signal can cause very unpredictable results. Power has to be clean. Digital signals are produced by a device with a power supply, applying the necessary voltages to a signaling conductor. Digital signals are commonly used as an output to turn devices on and off, typically through relays that switch the power needed to operate the devices. It's low voltage. Analog signals is a signal that is a little bit different. It has a continuous range of possible values between 2 points. Analog signals can convey information that has units of measurement. They can also provide a value between 0 and 100% for a controllable device. And we're going to talk much more about this. For example, if you're controlling a fan, 0% of the signal, the fan would be stopped. 100% of the signal, the fan would be at full speed. Any number in between is a proportion or a percentage of that range. The most common signals used are voltage, current, and resistance. Devices can use other analog signals as long as they're compatible in range with the sender and receiver and understand the values. Most common signals are 0 to 10 volts DC, 2 to 10 volts DC, 4 milliamps to 20 milliamps of current, 0k ohm to 10k ohms of resistance. So we have our voltages, our current, and our resistance. On the voltages, the only difference between the 0 to 10 and the 2 to 10 is the amount of range. Now, the reason we sometimes use 2 instead of 0 is it's very difficult sometimes to come up with 0 volts. Analog signals are different from digital as that small fluctuations in voltage, current, or resistance are meaningful. In other words, if you're expecting 2 volts to equal 65 degrees on a sensor, and you actually get 6 volts instead, it's going to do something entirely different to the system. Fluctuations that are not expected are called electrical noise. Electrical noise can cause significant operational issues and require careful placement and thought on cable runs, wire size, and grounding, and I want to add shielding as well. For example, running analog signal cables over fluorescent lights in a suspended ceiling will cause issues. Okay, believe it or not, wiring near fluorescent lights can pick up a lot of electrical noise. You can use shielded cable. Shielded just means all the individual wires are surrounded by usually an aluminum shield in the wiring. However, it still does not overcome the noise created by fluorescent lights. Digital and analog control systems are most often wired point to point. That means a control sensor wires to a specific point on the controller and no other device will share that same wire. No two devices other than the controller and one other device will share a wire. Additional wiring is needed for long runs because everything comes back to the controller, and signal loss can be a real concern. The longer the wire runs, the more voltage drop you're going to have, the increased resistance you're going to have, and this contributes to signal loss. So what we've done is over the years, a new format of signaling has been created. It's called protocol messages. This says that some control systems share additional information in each signal event. It takes on the form of what we call a structured message. The structure includes sending and receiving device information, basically addresses. If you want to compare it to a computer network, it's an IP address. The protocol or structure is implemented by both the sending and receiving devices. They have to have the identical protocol so that they can actually talk to each other. Each message on a protocol messaging system includes the sending device, the receiving device, a shared value identification. In other words, what are we measuring? Is it temperature, pressure, and what is the location? The shared value, okay, in other words, the actual numeric value, and any additional parameters. All components in a protocol messaging system are wired together in a typical network arrangement. Wires are run from one device to another, or from a controller to a hub to a device. In this arrangement, each device only listens to the messages that are addressed to them. All other messages are ignored. Some of the protocol messaging systems will use the building's LAN, which is the local area network, WAN, which is the wide area network, or other networking. They could be wireless. Some will use an independent network. Any device can communicate with any other device on the network as long as the protocol is identical. So let's talk a little bit about what we talked about in this presentation, just as a quick review. Okay, we talked about the different types of some terminology. We talked about control devices. Okay, we talked about sensors. We talked about mechanical and electrical sensors. We talked about the controllers. We talked about some of the output devices known as actuators. We talked about the 3 types of actuators, the relays, the solenoids, and the electric motors. We talked a little bit about the human-machine interface. All of this we're going to talk more about. We talked about the types of control systems, the digital signal, which is on or off, the analog signal, which has a range. And then we talked about the newer type of signal, which is the protocol messaging, which allows devices to all share a common network and talk to each other as well as talk to the controllers. and they use a protocol structure. We're going to now, in future recordings, we're going to dig into each of this areas a little bit deeper, and we're going to talk a little bit more about signaling and what the different sensors give.